Alright, so let's talk about a topic that's kind of, in my opinion, a little bit weird, but it does actually occur, and this is the idea of carbocation rearrangement. So, let's say we're running a reaction and we do something like an SN2 react. We do an SN1 reaction where our leaving nucleophile pops off and we end up with this carbocation. So, in this structure, I've drawn a primary carbocation over here. I'm going to keep the charge beneath it just to keep the diagram clear. And if this was all that happened, it would be a pretty by the numbers reaction, but what we can get is we can get a shift this methyl group or another carbon group, usually methyl group, over to replace it. So why and how does this occur? Well, first of all, it's going to occur because it stabilizes the carbocation. So right now, this primary carbocation is super unstable. How it occurs is a bit of a, well, it's a little bit of a hand-waving explanation, but let's talk about it. So right now, this positive charge is being held up by a vacant p orbital. So this p orbital in carbon, we have the sp2 carbon, sp2 hybridization taking care of this bond, this bond, this bond, but right now there's an open p orbital. Now, if we were to look at the carbon beside it, this is sp3 hybridized, so if we were to guess at the electron density, it would look sort of like this. And if we were looking at the CH3 group, the sigma bond orbital, that sp3 hybridized orbital, looks sort of like this. So we have three orbitals beside each other that sort of look like p orbitals. Now to make this shift, what they're going to do is they're just going to lean over a little bit. And as it leans over, this methyl group here is not actually going to be bridging between these two carbons. So they're going to use, this one's using its hybridized sp3, this one's using its vacant p in order to form basically a 2-electron 3-center bond. Now this is not predicted by Lewis theory. Lewis theory cannot explain this. So this is kind of borrowing from MO theory to make this explanation. But what's going to happen is that this CH3 group is going to start tilting over and they're going to form a short-lived 3-carbon intermediate. Now this is our transition state, and to make it happen we need something small, so we're likely to only see this sort of with a methyl group shift, nothing bigger than that. Now there isn't high energy to this, so if we were at low temperatures it's not as likely to occur. High temperatures is going to happen more quickly, but generally if we've got a primary carbon there's a driving force for this. But anyway, it leans over, moves all the way across, and what we end up doing is creating a new carbon-carbon bond and moving the carbocation from our primary over here to create a secondary. So this is what's called 1-2 rearrangement. We have one carbon, a second carbon, your 1-2, and the alpha group shifts from the second carbon to the first carbon in order to relieve the strain of having a primary carbocation. Now, can this happen again? Well, the answer is yes. So I've drawn the structure. We have a terp-butyl group here. So in principle, we could take this CH3 group, move it over here, and create a tertiary carbocation. But the reality is this doesn't occur very much. And the reason it doesn't occur is that one, there is a transition state blocking this. So it takes sufficient energy to jump over. The odds of you jumping it twice are very small. The other is that typically our reaction completes before it has a chance, because there is, once we get to this point, we're back to a reaction intermediate. It is somewhat long-lived and long-lived enough to react away. But big picture here, when we have primary carbocations, especially if we have primary carbocations, what we will see is a 1-2 rearrangement. A neighboring methyl group will move over to this primary carbocation if it creates a secondary or tertiary carbocation in its place. And the reason for this is to stabilize the carbocation. So this is the messiness with an SN1 type reaction. When you create a carbocation, especially a primary one, there is a good chance that you end up getting a rearrangement and you're not going to get a substitution of the carbon that you were hoping for.